So now that we've gone through the basics of some of the ways that some of the circuit logic that you might want to construct using CMOS and how to hook up transistors in order to perform that logic, I'd like to start getting into how will we actually fabricate or create these types of circuits in an actual integrated circuit or on a silicon wafer. So again, CMOS transistors are fabricated on silicon wafers for the vast majority of all integrated circuits. And what we do in order to try and get the logical functions and connections that we need is we use a photolithography process similar to how a printing press would work, and use different steps in that process in order to, for each step, we're either going to try and deposit different materials or take away different materials in order to construct a set of connections and all of the different source and drain regions and everything that we need in order to produce the transistors and the connections between the transistors. So the easiest way to understand is by trying to view both, sometimes from the top as if you were looking down on the wafer, and sometimes viewing a cross section of a wafer as if you had like split the wafer, like actually snap the wafer in half, and you're looking at the cross section of the wafer. And in going through that manner, we're gonna, in the next several foils, we're going to go through and look at how a very simplified manufacturing process would happen in order to create some of these transistors and circuits. So here's a view of what a typical inverter cross-section would look like if you split the wafer and are looking at the cross-section of what the process would look like. So in this case, typically most fabs will use a P substrate. So the wafer as a whole is a P-type wafer, and they'll start out with that as what we call the substrate. So the wafer itself is P-type material, and since the wafer is P-type material, you would construct NMOS transistors in that wafer. So you can see on the left-hand side of the diagram, we have an NMOS transistor where we have two N+ regions that are formed in the P substrate that will form the source and drain of the NMOS transistor, and then we'll have over top of the area between the source and drain of the transistor, we'll have oxide for our gate oxide, and there will be polysilicon deposited for the gate of the transistor, of the NMOS transistor. In order to construct PMOS transistors, you need to do that in N-type material. So the substrate itself does not have N-type material. So what they do is they'll create an what they call an N-well. So it's basically a sort of deep, compared to the source and drain, it's a deeper well of N-type material that they will diffuse into the substrate. And then after they diffuse that N-well into the substrate, then they will implant the P+ material that are the source and drain. So on the right hand side of the diagram you can see the PMOS transistor labeled there. Those two P+ regions for the source and drain will be formed, and then between those two regions, again, they'll deposit a gate oxide underneath a polysilicon gate. The polysilicon will be used as the gate material for the PMOS transistor. And so here you can see an NMOS transistor created, PMOS transistor created inside of an N-well, And then if we're creating an inverter here, we want to connect the P drain of the PMOS transistor through metal to the NMOS transistor, but we don't want that metal shorting to anything else, so we don't want it shorting to like the substrate, for example. So we'll have to deposit some silicon dioxide insulator and then deposit the metal on top of that. And then the source of the PMOS transistor will be connected to metal and connected to VDD, and that's on the right hand side of the diagram. And on the very left hand side, the source of the NMOS transistor will be connected to metal and connected to ground someplace else. So this is a quick, relatively simplified cross-section of how we would eventually construct an inverter from just simple N and P type silicon and metal connections and polysilicon for the gate. So one of the things that I didn't show in the previous slide is the connections for the body of the transistors. If you remember from, a lot of times the body connection is not shown in our circuit diagrams, but the body connection always needs to be connected. Otherwise, you're going to run into problems of various sorts. So this is showing that same inverter diagram, but with the additional connections for the body connections of the N and P devices. So in order to connect the NMOS device, which is on the left hand side, the body of the NMOS device is the P substrate. So that means we need a P plus type material to connect our metal to. And if you remember, the P substrate for NMOS devices should always be connected to ground, or the lowest voltage in the circuit. So we will connect that to the same voltage that we connected our source of our source of our NMOS transistor to. So it will be connected to the same metal ground connection. And then for our P-type transistor, which has an N body, which is the N well, we need a connection to the N well. So the connection to the N well will have to be an N plus type material so that it connects well to the metal, and that has to be diffused into the N well. And again, because it's an N type diffusion for the PMOS transistors, we need that connected to the most positive voltage in the circuit, which is our VDD connection. So through the metal, the same metal that's connected to the source of our PMOS device will also be connected to the well tap of our PMOS N well. And so that's the VDD connection on the very right hand side of the diagram. So we use the heavily doped P plus material or heavily doped N plus material in order to get a good connection between the semiconductor and the metal. Because if you have metal lightly doped semiconductor, you don't get a good connection to metal. You'll get what's called a Schottky diode. And so we have to make sure to use a very heavily doped material for our substrate tap and our well taps and our source and drain connections. We always use heavily doped material in order to get good connections to metal. So now that we've gone through what the cross-section of our inverter structure looks like, let's look at a little bit how would we go about actually fabricating something that has that structure to it. So as I said before, we use something called photolithography in order to try and build up and tear down material in such a way that we get the structure that I just showed in the previous two foils. So the photolithography, in order to create the transistors and wires, we generate what are called photolithography masks. And that's basically just a way of saying we create layers that can be drawn out, and the cross section of those layers will block out regions that either light will hit or light won't hit. And by hitting certain regions, when we develop the material in that region, we can either take material away or keep material there. So here I'm showing all the different layers that we're going to need in order to create the structure that we just talked about. So first of all, we're going to need, starting from the left-hand side, we're going to need some metal that will basically connect to ground. So that's the blue wire, or the blue region that's kind of drawn out on the left-hand side, which is called ground. And you can see there's two other blue regions that are drawn out. One is our connection between NMOS and PMOS transistor, which is our connector Y. And then there's another one on the right-hand side, which is our metal connection to the VDD for the well tap, and the connection to the PMOS transistor. So that covers kind of our metal connection that we saw. We'll also need connections between the metal and the diffusion regions, which are the PMOS and NMOS, P plus and N plus diffusion regions, which are either the substrate taps or the connections to the source and drain of the transistors. Those are basically the big black squares that you see. So on the left hand side, you'll see there's a big black square over the substrate tap and over one of the NMOS transistor connections, over the other NMOS N plus region, and then there's three on the right hand side, which are the connections to the PMOS transistor source and drain and to the N-well connection. So those big black solid squares are basically via connections that will connect between the metal and the substrate, or the silicon. Next regions that we need, you can see the red striped region is the polysilicon that will be deposited. Polysilicon is got reasonable conductivity to it, so it's not as it's more resistive than metal is, but it can be used pretty well as a conductor, especially for short distances. So we use that polysilicon to both define where our gate regions are for our NMOS and PMOS transistor, but also to connect those two gate regions together between each other. And then finally, well, not finally, but next we have the N plus regions. So the N plus regions are the solid green regions, and those are around our N plus for our NMOS transistor on the left side, and the green region on the right hand side, which is N plus connection to the N-well tap. Then we have the P plus regions, which are the orange ones. There's one on the left hand side, which is a P plus connection to the substrate, and then the two that are more on the right hand side are P plus regions for our P plus source and drain of our PMOS transistor. And finally, the next connection is, or the next region is the more grayish region that's kind of around the PMOS transistor and PMOS well tap, which is the actual N-well region. We need to define the area around the PMOS transistors in order to diffuse the N well into the substrate. And you might be wondering what the black dashed line is that's going across the entire figure from left to right. That is basically showing where, if we cut this from the top or split this, this is where the cross section that we were looking at earlier is actually looking at. It's looking at the cross section along that black line. If you cut through and then rotate it up 90 degrees from the, you basically see that type of cross section. So this here is showing what I talked about in the last slide, where I was saying we need all these different type of masks. This is showing what each mask itself would look like instead of having them all on top of each other. So if we took each of these dashed lines and the shape that is over each of those dashed lines and pushed all of the dashed lines together and pushed all the shapes together, it would look like what was in the previous slide. So again, the gray is the N well, the dashed or kind of dashed red region is the polysilicon. The green is the N plus diffusion mask, what it would look like. The orange is the P plus diffusion mask. The black is the contacts from the metal to the substrate or silicon. And then the blue dashed lines are where the metal would be deposited. So this is just showing the inside of what a fabrication facility, modern fab facility looks like. Our IC chips are built in really huge factories that are called fabs. They contain what are called clean rooms that are basically as large as football fields or potentially larger. They are required to have very, very, very little contamination inside of them, because when you're talking about the dimensions of transistors, if you have even potentially one transistor, if it's the right critical transistor on a integrated circuit that has 8 billion transistors, one transistor could cause it to fail. And that one transistor is as small as, if you keep in mind, around 40 to 50 atoms. So any amount of dust would be critical. It would be huge and destroy an integrated circuit. So these are called clean rooms for a reason. They have ultra good filters, and for the most part in modern clean rooms, even though you see people walking around in there, the actual silicon wafers that are going through the clean room stay inside of the machines almost all the way through and never actually interact with humans, from the standpoint of we give off way too much contamination for modern microprocessor processes. So it's kind of interesting, but we're not going to go into that too much.